So let's start talking about asymmetric cryptography. Asymmetric cryptography. So far we talked about symmetric key cryptography, in which Alice and Bob had the same key. That's why it was symmetric, because they had the same key. In asymmetric key cryptography, they won't have the same key. They'll have different keys. And the reason is that it's actually quite hard for Alice and Bob to share a secret key and no one else to know it. Right? How did they get to share that key? Well, maybe they met in person, they agreed on the key without anyone seeing it, and then they went on their own ways. But that's burden, right? Having to meet everyone in person to share a key with them. For example, whenever you surf the web or you go to bankofamerica.com, you have to meet in person someone from Bank of America to agree on a key. Right? That's very inconvenient. So asymmetric key cryptography tries to resolve this issue and tries to make parties who don't share any secret key together still be able to communicate securely. And it's used widely in secure communications today in TLS, which we'll talk about later in the class. Basically, whenever you go to websites having sensitive information, you are actually using asymmetric key cryptography as well as symmetric key cryptography. Okay. So we have Alice and Bob like usual, but this time they're going to have different keys. So Alice is going to have a key pair, which is a pair of a public key and a secret key. Okay, so this is a public key pair. Now, the public key is known to everyone. Okay, so including known to Bob, but also known to the attacker, let's say Eve. Okay, everyone knows the public key of Alice. Now, the secret key of Alice is known only to Alice. Okay? And similarly, Bob has public key Bob and secret key Bob. Again, the secret key of Bob is known only to Bob, and the public key of Bob is known to everybody. So in some sense, Alice doesn't share any information that's secret with Bob. She knows Bob's public key, but so does Eve. Eve also knows Bob's public key. Okay. So now, when Alice wants to send a message to Bob, what she does is she encrypts the message with Bob's public key. Okay? So she encrypts the message with Bob's public key and obtains a ciphertext, and she sends the ciphertext to Bob. Okay? So the public keys are for encryption. Okay? Anyone can encrypt to Bob because all you need is his public key. So in particular, Eve can also encrypt to Bob. But only Bob can decrypt. Because to decrypt, you need the secret key. Okay, so when Bob gets this ciphertext C, he uses the secret key, his own secret key, and decrypts it to obtain the message M. Okay? So you decrypt with the secret keys, but you encrypt with the public keys. Is this clear? Any question on this setup? Okay. So then, like we did for symmetric key encryption, let's talk about the syntax or the API of the encryption scheme. Well, it consists of a key generation algorithm. The key generation is going to produce not one key, but a key pair. Then it's going to have an encryption algorithm that encrypts a message under the public key. It's going to have a decryption algorithm that decrypts using the secret key, a ciphertext, and obtains the message M. In terms of correctness, okay, so we have correctness and security as properties. In terms of correctness, very similarly to symmetric key encryption, for all the messages M, for all secret key and public key that are output by the key generation algorithm, we want that if C is the output of an encryption of message M with public key, then basically when you decrypt the ciphertext using the corresponding secret key, you get M. Okay, so you always get M.